about the losses that occur in pipe systems and the laminar and the turbulent regime, and then boundary layer. It's a different concept, but we have said that the reason for the losses is the boundary layer. Now I'm going back to loss coefficients, and now I will talk about the pressure drop. It is only due to minor losses. So what happens in minor losses? Okay, and to understand it, so I have an example here. So that pipe section suddenly drops. So you have an area 1 here, a large area, and then you have the small area. So what happens to pressure value? What happens to velocity? So first, let's look at the velocity values. Okay. Actually, let's start with the pressure one and then talk about the velocity. So the pressure at point 1, the fluid starts with P1 here. Okay, and then this P1 at point 2, you can see it here. Okay, at point 2 drops the minimum value. P2 is minimum. Okay. So why the P2 is minimum? Because that area suddenly changes. Okay, this area suddenly changes. You can see these are the trajectory. These are the trajectory of the fluid particles. This fluid particle travels in that way. This fluid particle travels in that way, and then it goes that way. You can see the outlet, and this is the center line. This fluid particle travels in that way, and this fluid particle travels in that way. And then you have the fluid particle here that travels in that way. Okay, these are the trajectories. And the P2 is the minimum one because the area changes and the fluid accelerates. Okay, but as it accelerates, it that converts with an area, which is area 2, which is less than the actual area of the shape of the pipe. So you can see the fluid area here, the fluid flows, this one, and as well as this one. Okay. This area, which is at point 2, area 2. This area is smaller than the area of the pipe section. Area 2 is smaller than actual area, you can see, of pipe. This one is smaller than the actual area of the pipe. And then, so this small area is due to acceleration of the fluid particles. When they enter smaller cross-section, smaller diameter area, they accelerate, but as they accelerate, they are coming together, they are decreasing the area because velocity increases. So this area decreases, so that, not this area, but general area here. The area of the fluid particle, they are traveling at this location. It was an area of this part, but when you move to another location, this area is that amount. Okay. And then you have this amount of area. Okay. So the area change. So let's say that this one is let's not put the numbers here because it will be more. So that area change due to acceleration, okay, or velocity increase. So if you know that, for that rho AV is constant. If it is water, for water, AV is the constant. Okay. So if the velocity increases, the area should drop. Okay, but that area drop continues, and you get the smaller area than the actual area of the pipeline. And this smallest area happens, you can say decreases. It changes, but it decreases. And the smallest area where you have that maximum velocity is called the vena contracta. Okay. Now for the point 2, you have the minimum pressure. Okay. And then now comes the deceleration part. So till that location, you have the acceleration. So this part. from inlet from 1, you can see from 1 to 2. Okay. This part is acceleration. Okay. Now comes the deceleration. Okay, the deceleration part is not so efficient as the acceleration part. If you remember the last lecture, so I have talked about this one, so I will just show the slide. So fluids can be accelerated efficiently, but the deceleration is a problem, okay? Because if it accelerated, then the deceleration will not be so efficient as that one. So the pressure drops to minimum value, okay? You have the pressure drop to a minimum value, and then the pressure starts to increase again, because now the deceleration part comes. Pressure increases, but the problem is it never gets its initial value back. So it increases and increases. It never gets it back because you have velocity increase, that's okay. But there is some part of the energy that we cannot get it back. Now you will see what is that part of the energy. Okay, so this is the first part of the problem, that you should know that deceleration is not efficient. Okay, not efficient. Okay. And this part is efficient. That is always the same case. If you go fast with your car, acceleration is very easy. You accelerate your car and you move very fast. But when it comes to stop, that is a problem. Okay, stopping is not so efficient as the acceleration. Okay. The same happens with the fluid stems. Okay, now the deceleration part is not so efficient. Now you will see why it is not so efficient. The first problem is that you can see that fluid particles here, they are not traveling. Okay, they are rotating. You can see these are rotates. Yeah, this one's not, let's say rotates, but circulates. Circulates is a better term than rotates for this case here. So you have the circulating flow. Okay, here you have also the circulating flow. And you can see there is a trajectory that for a fluid particle, it's shown here. You can see this part of the flow, as well as that part of flow. This part, and here that part. Okay. And it's separated by this line here. Similarly by this line. Okay, and the part that is present in these symmetric parts, you can see it doesn't, so that it doesn't go with main flow, doesn't go with main flow. Okay, so they are not going with the main flow. You can see that they are always here. They are rotating, recirculating here and recirculating here. Now my question comes to you that, so it is recirculating, there is a recirculating. Where does that energy come from? Okay, where does the circulating flow get energy from? So how can you tell me, where does that energy come from? This recirculating flow, where does it get energy from? Let's see, what's your idea? You can write your idea as a comment. Friction, no, of course no. Friction does not provide the circulation. Friction is opposite, it stops the flow. Okay, but there is some source of energy. There is no pump, you can see there is no pump, but there is some source of energy that these fluid particles get and circulate here. From wind, there is no wind. Can you see any wind here? Kinetic energy, yes, of course, kinetic energy. Okay, it doesn't go with the main flow. It uses kinetic energy of, not kinetic energy, but general energy. So it uses energy of main flow. For recirculation. So you can see it doesn't go with the main flow. This is the main flow. You can see it. It doesn't go with it, but it recirculates here by using energy of the main flow. And this one is the loss. This one is the loss. Okay, this is the reason for we are having the loss. Okay, now let's go back to our chart here. So this is the P1, the maximum energy. At point 1 here, V1 is 0. So let me P2 is minimum. So these are very important steps. So this is the one important. And the V1 is 0, okay, because it is far, it is not exactly 0, but it is approximately 0. Okay. It is away from inlet. It is far away from inlet. Actually, outlet. This one is the outlet. Far away from the outlet here. Okay, and since reservoir, the velocity from outlet, and therefore V1 is 0. This is the off reservoir. Okay, so this pipe is connected to a reservoir. This is what the V1. Okay, and therefore, by the Bernoulli's principle, this pressure should be constant. It shouldn't decrease. So it should go some way like that, if it is ideal. So by Bernoulli's principle, because that Z1 is same as Z2 and is same as Z3. But as the Bernoulli says that P1 plus rho V1 squared by 2 plus rho GZ1 is equal to constant. And for our case, Z's are the same velocity at point 1. So it is not the velocity at point 1 is 0. Therefore, the pressure should remain constant by Bernoulli. Okay. This is by Bernoulli. Pressure should remain constant because V1 is 0. Z1 and the Z2 Z3 are the same. Therefore, I can take the Z1 as reference. It can be 0. If I take Z1 as reference, P1 should remain constant. Okay. But it doesn't remain constant, but you can see that this one is for ideal, but in reality, you have this one. Okay. It starts to drop after point 2. You can say this one is the point 2, and after point 2, it starts to drop. Okay, and this part is the losses. Okay, and that loss is equal to K into KL. This is the loss coefficient into V squared by 2G. Okay, this is the loss coefficient. Okay, so if you are looking for as the loss coefficient in pressure terms, you should multiply it with this quantity with rho G. Okay, so if you multiply with rho G, you will get the pressure terms, the unit as pressure. Okay, so we can put it as here, or it will be that KL rho V squared by 2. They are the same stuff. This one is meters and this one is the pascals. Now my question comes to you, what is that energy here? Let me show that energy to you. Let's get your ideas. What do you think this energy here is? So this one is P1. Okay, that is the pressure line. You can see that this pressure line diverges, and there is one more energy here. What is that energy? So let's see your ideas. So you can see that this energy increases and increases and then decreases. What is that energy? So this one is the pressure line. So I should show it very clearly here. This one is the pressure line. Pressure. So what is that difference between ideal one minus the pressure? What is that difference? What is that energy? Flow energy? No, I mean what type of energy is it? Kinetic energy, potential energy? What is that? Flow energy, internal. No, internal, where do we? So if you start from point 1, you look at the picture here. So the velocity at point 1 is 0. You can see far away from outlet, and it is off reservoir velocity. Okay, velocity here is 0. You can see, but there is pressure. But as you move into the decreasing area parts, you can see something increases and the something drops because it should be in accordance. So that pressure drops, and see this one is the ideal line. If it is ideal, it should be constant. Total energy. This is the total energy line. So this one should be constant. But in reality, it doesn't happen. So there is losses. Okay, this one is okay. But there is also that the pressure drops and something increases. What is that something? So that what does the fluid gain as it moves from point 1 to 2 and the point 2 to 3? What it gains? Kinetic energy. Of course, kinetic energy. And that one will be the velocity kinetic energy of the fluid, it will be rho v squared by 2. Okay, and similarly here, you will have that rho v squared by 2. Okay, similarly here, okay, rho v squared by 2. Similarly here, okay, rho v squared by 2. Okay, so this is the, you can now see that this is the ideal one. If it was ideal, the pressure should remain always constant. But in reality, after point 2, you have drops, losses. This is KL V squared by 2G, or KL rho V squared by 2. And in reality, this is the total one. That total one is two parts. One is due to pressure line, which is this one, P1, and one is due to kinetic energy, which is that one. Okay. So you have two sums. That one plus the pressure one is total energy, and plus these losses, you will have the total pressure for the ideal one. Okay. Now to find the loss coefficients for these pipe components, we have said it is minor losses, and the minor losses is equal to KL multiplied with V squared by 2G. Okay. These are the minor losses, and then there are different minor loss coefficients. KL is a minor loss coefficient. Okay. For that elbow, you can see if it also matters whether it is flanged or threaded. They have different, they have different flow coefficient, minor loss coefficient. If it is flanged, you can see the value is very small, 0.3. But if it is threaded, you can see it is very large. Okay. But the reason is that these threads that you are putting in the flow direction, it increases the loss coefficient. Okay, these threads are, like obstacle in flow direction. And you can also have that the radius here, that if you have larger radius, if you have longer radius. And then also you have the bends here, 180 bends. So this one is 180 bends. And for 180 bends, you can have flanged case as well as the threaded case. Okay. And these are the loss coefficients, and for that, again, flange and the threaded. So let me show you one. So that one flange and one threaded case. Let me see if I can find. So I hope you can see that we have seen this flange. So let's see. There is flange, and you can have also that threaded. Let me show that one too. Some minutes, and now you can see that you can see the window. So you have the two types of the connections, and the one is the flange. You can see that flange. We are connecting the two pipelines with a flange here. You can see it. And the other one is the threads. You can see that threads. These are creating obstacle. Okay. So therefore you have that larger KL. Okay. If you connect two pipeline to the two sections together, you can see that the next section will be an obstacle due to these threads. Okay. This one is larger KL, but in the flange version, you can see flange. We not create an obstacle in the flow direction. What you are doing is that you are connecting the pipelines with mouth to mouth each other. Okay. Therefore, you don't have any larger KL value, but here you have the smaller KL. Okay. So here, no obstacle in flow direction. No obstacle in flow direction. Okay. Good, and we have the T's, and you can see that T section here. This is in the shape of the T letter. and there are also flanged threaded parts, and you can have that unions, you can see the unions, and the valves, you can globe valve and angle valve, gate valve, swing check valve, ball valve, okay, different valves, and the different flow coefficients. Okay, all of them are from Manson et al. Now let's solve the example here, and we will have an example. And before solving the example, I will just summarize it. You have two types of the losses, and one type of losses is the major loss, and the major loss, you can write this one as F L by D and the V squared by 2G. And the next loss is due to minor losses, and the minor loss will be KL V squared by 2G. And the total is the sum of this one. One more thing I should tell you is that if you have that outlet, so you can see this outlet, this is the reservoir. Okay, for this outlet into that reservoir, and the reservoir has a velocity 0. Okay, and this fluid here has a velocity of V out. This outlet velocity is dissipated inside that reservoir, because that reservoir will have the 0 velocity. It means that this outlet velocity should be 0 after some distance. Okay, so at the end, finally, the V out will be 0. Okay, so that it means that all kinetic energy is dissipated, and KL will be 1. So all kinetic energy of the fluid is dissipated. So when the fluid enters into that pipeline, if it has the kinetic energy of V squared by 2, and at the end, the velocity will be 0, because it comes to a reservoir with a 0 velocity. Therefore, all of this is dissipated as the friction, due to friction. It is dissipated. And then, due to that dissipation of all kinetic energy, here you have the KL as 1. If you put the KL 1, you will see that the minor loss is V squared by 2G. That is equal to kinetic energy of the fluid. Okay, good. So these are the two important results. Now we can solve an example. The first example is that we have a tanker here, a vented tanker. It is to be filled with the fuel oil with a reservoir, so with a density of 920 kilograms per meter cube and the viscosity of 0.0545 kilograms per meter second, from an underground reservoir using a 25 meters long, 4 centimeter diameter plastic hose with a slightly rounded entrance and the 290-degree smooth bends. Okay. So let me write the values here. So the length is 25 meter, and then diameter is 4 centimeters, and the material is plastic hose. Okay. And with a slightly rounded entrance. So these are the slightly rounded entrance and 290-degree smooth bends. These mean that you have to use the KL. Okay, KL. You should look for that slightly rounded entrance, and you should look for that KL for this 290-degree bend, smooth bends. And the elevation difference between the oil level in the reservoir and the top of the tanker where the hose is discharged is 5 meters. You have this 5 meter distance. The capacity of the tanker is 18 meters cube, so that the volume of the tanker is 18 meters cube. And the filling time is 30 minutes, so the time is 30 minutes. Taking the kinetic energy correction factor at the hose discharge to be 1.05. Okay, so I will talk about this one. Assuming an overall pump efficiency of 82%, determine the required power input to the pump. Okay, now let's solve it. Okay, so to solve it, I will first write the energy equation. The energy equation says that since it is a steady flow, this one is steady. Steady, if you remember, is that the total ins are the same as total out. We have the total in same as total out. And then I can write the equation so that mass flow rate, okay, or even you can divide by all of the terms with mass flow rate, and you can write this one as a P1 plus rho V1 squared by 2 plus rho G Z1. Okay. And the plus, that is the pump. You have that. So let me write these quantities as that with mass flow rate, so that you will have that m dot and the P1 by rho plus V1 squared by 2 plus GZ1. Okay. Plus that the work dot of the pump, which is useful, that one should be equal to, this one is there is a pump here, and that one will be equal to m dot and the P2 by rho plus V2 squared by 2 and plus GZ2. This is the energy equation. Now let's take the points, so that point 1, so it is top of the reservoir. Okay, this is the point 1. This one is point 1. Okay. And then you have to take the point 2, that one as the outlet of that discharge hose. Okay, this one. You have taken the outlet as here, the discharge of hose. Okay. The outlet of this one is the point 2. In that way, the height will be constant. It will not change, 5 meters. Okay. But since, again, it is the ventilated tanker, this outlet will be also the 1 atm. So as we have said that 1 atms are the same, so therefore P1 and the P2 is same. So here it is, again, let me note it, P is 1 atm, P atm, since ventilated tank. Okay. Inside the tank, you have 1 atm. And now comes the velocity at 1. Since it is reservoir, the velocity 1 is 0. The reservoir. And then you have that V2 is 0. V2 is not 0. V2 was 0 in the previous case. In the previous case, V2 was 0. But the problem with the previous case was that if I take, for example, the height as the reservoir height here, this reservoir height will change because the tank is not so large. It should fill. As it fills, you can have the height change, and this height will be a time constant, time variable value. Therefore, it is not a good option to choose the reservoir. The better one is that outlet of the discharge hose, pressure P. Okay, so that the V1 is 0, and the Z1, you have said it. So you have somebody resolve that the Z1 is also 0. This one is 0. Okay, and the work dot pump useful, and the m dot V squared by 2 plus GZ2. And I've forgotten to add one term, which is that losses. It will be plus m dot GHA, losses term. I forgot to add it. Okay. Now the question itself says that take kinetic energy correction factor at the hose discharge to be 1.05. So let me write the equation again and take the kinetic energy correction factor. So it means that do not write this one as V squared by 2, but you should write this one as 1.05 multiplied with V squared by 2. Okay. You should take a correction factor here in front of the kinetic energy, and it is 1.05. And then plus the GZ2. Okay. And then plus m dot GH. Okay. Now everything will be okay. So to solve that equation, I should know the velocity at 2, at outlet here. I should know the Z2, which is 5 meters. Let me do that 1, 2. The velocity here, it is 5 meters. And I should find the HL values. Okay. Let's start one by one. And to find the velocity is easier. I can find it. Let's find the velocity. Then the question says that for 18 meters cubed, we need 30 meters. So that V dot will be equal to volume divided by time. And for 18 meter cubes, we need 30 minutes. And the 1 minute is, so you will have the 1 minute is 60 seconds. Okay. And therefore you will have that this one will be, you can tell me the final value for V dot. So From this v dot, I can find the velocity. So that will be easier part. V dot volume flow rate is velocity into area. Okay. What is the V dot value? Zero point zero one. 0.01 Anar Abdurrahmanlı per second. Ali, okay. So this is the V dot. Now I'm trying to find the velocity at 2. Okay, this is the discharge hose here. You can see it is outlet of discharge hose. So that velocity at 2 will be equal to volume flow rate divided by the cross-sectional area. This one is 0.01. And the volume, the diameter is 4 centimeters. Okay, you can see it will be pi d squared by 4. And then you will have 4 multiplied with 0.01 and divided by pi multiplied diameter, which is 4 centimeters, will be 16 times 10 to the negative 4. From here, you can give the value of the velocity. Looks like it will be a large amount of velocity. .95 meters per second. Okay. Now we have finished the velocity part, which is 7.95 meters per second. So now comes the HL part, the head loss. To find the head loss, if you remember, we had the formula, okay, so you will use FL by dV squared by 2G. And to find the F, so this one is for the turbulent flow. I think I have not told you that. So these equations are all for turbulence. So turbulent. Okay, these are all for turbulent equations. F is the turbulent flow equations. But if it is a laminar, now let me summarize it here. And to find the F, first the equation itself, you will have two types of the losses here, and the HL will be equal to HL major plus HL minor. Okay. And to find HL major, to find it, first you should determine Reynolds number. Okay, should determine the Reynolds number. And it comes that the Reynolds number is laminar. Okay, if it is laminar, okay, F is 64 by Reynolds number based on diameter. But if it is turbulent, you have to use the Colebrook equation, or you can use that is the Haaland equation, or you can use, if it is smooth, you can use the Blasius equation. Okay. Therefore, we should determine the Reynolds number, because F is, I've said it here, F is function of the Reynolds number and the relative roughness. If the Reynolds number is small, then you will have the laminar flow. If it is large, you will have the turbulent flow. Now let's therefore find the Reynolds number to find the HL major. The Reynolds number is that density, velocity, diameter divided by mu. Okay. The velocity, we have found it. Density, let's see if it is given. Yes, 920. 920 multiplied with 7.95 multiplied with the diameter, which is 4 centimeters, and it divided by the viscosity of the flow, which is 0.045. Now you can tell me the value of the Reynolds number to solve that we're sure that if it is a laminar flow or it is turbulent flow. But this one has high viscosity, but we cannot know it if it is laminar or turbulent. Let's calculate it. So 6501. Okay, this one is the Reynolds number. It doesn't have any dimension. Okay. And is this laminar or turbulent? This is my question for you. Is it laminar or turbulent? Of course, turbulent, Ali. Yes, it is turbulent. Therefore, I have to use one of these equations. Okay, now let's go back to these equations. But before going back to equations, there is a plastic hose. This one is a clue. You should know the material. This is plastic. So you can also use the, so I forgot to add it, or the Moody chart. Moody chart. Okay, I will use the Moody chart as well as the required equation. But if you go back, first the Moody chart. So for the Moody chart, it is not shown here, but for the plastic, if it is plastic, the epsilon is taken as 0. Okay. For that plastic pipes, epsilon is 0. Therefore, it is taken as the small. For plastic pipes, epsilon is 0. Epsilon is 0, and therefore the problem is here smooth. For the smooth equations, you can see that epsilon is 0. I can use the Blasius equation, which says that F is 0.3164 divided by Reynolds number to the power of 0.25. And F will be 0.3164 divided by Reynolds number to the power of 0.25. Okay, and this one will give you the Reynolds number is 0.3164 6501 to the power of 0.25. Okay, and you can tell the value of the friction factor F. So this is by equation. So I will also use the Moody chart, and you will see that the Moody chart is not so accurate method to find the friction factors. 0.03. This is the F friction factor. Okay. Now let's go back to the chart here, the Moody chart. For finding the value in Moody chart, firstly, I should take the epsilon as 0. You can see the epsilon by D should be 0, relative roughness. There is 10 to the negative 6, the minimum roughness, but there is a line that is shown with here, smooth part. You can see it, it is given. Smooth pipe. So I need smooth pipe and the Reynolds number, which is 6501. In other words, it means that 6.5 times 10 to the power of 3. Okay. And this is 10 to the power of 3, and it is 1, 2, 3, 4, 5, and 6, and 7. You have here 6.5. Approximately, but you can go that way. Okay. So I will go to that way and intersect the first line. So you can see smooth pipeline. So this is the smooth pipeline. It goes in that manner. Because this is the last line here. Okay, for that last line, I will find the relative roughness. Sorry, that the friction factor here, and that friction factor now will be equal to, if you do that, the friction factor is now okay 0.035. Means that this one is F by Moody chart. F value is 0.035. Okay. I don't know who, but you should know that the equation is better. Okay, this one is better. Okay, so then now comes to find the HL major part. Major part will be F L by D V squared by 2G. F is 0.03, okay, and the L of the pipeline section is, where is that L? 25 meters, and the diameter is 4 centimeters, 4 times 10 to the power of 2. And the velocity is 7.95 meters per second. And from here, you can calculate the major loss. You can tell me the value of the major losses. And then we will calculate the minor losses. Okay, so in that way, I can go to the chart here and to show the values for the minor losses that is given in the question. I should find the minor loss coefficients. So the true answer is 60.3 meters. Okay. Now comes the HL minor here. HL minor. And the question says that one has a formula KL V squared by 2G. Okay. And the question says we have a slightly rounded entrance. Okay, this is the first part, and the two 90 degrees smooth bends. Okay, this is the second part. So we have to look for, there are actually 3 KL values. KL, I should look for that slightly rounded entrance, and the plus KL for 90 degrees bends. We should look for 90 degree bends. But this is 2 times. I will take one of it and multiply with 2. So now let's see that window for that smooth pipes. So now you can see the screen with the loss coefficients. Okay, so you can find these loss coefficients at any book. For that slightly rounded entrance, so you have that, you can see for slightly rounded entrance, KL is 0.12. Okay, this is for the slightly rounded entrance. Now the next part is that to find for that 90 degrees smooth bends. Solve it. Now let's find that smooth bends. I should go that one to, so bends. Okay, 90 degrees smooth bends. You can see there are also mitre bends. You can see the change in shape. But the smooth bends, you can see it is not the abrupt, but this one is abrupt change with 90 degrees. And the flanged and the threaded, so that we take the flanged option here. Okay. Flanged option, which is 0.3. It is not stated in the question which one is the given, which is flanged or threaded, but we take the flanged option, which is 0.3. Okay. So then, now we will see the, so we have taken the value of the KL for slightly rounded entrance, which was 0.12, and the KL for 90 degree bends, which is 0.3. And we have 2 of them. Okay, I should add it here, which is for threaded. Okay. And I have 2 of them, therefore I multiply with 2. And therefore you will have that 0.6, 0.18 multiplied with 7.95 squared by 2 multiplied with G. Okay. Now you can tell me the value of the minor losses, and let's see if it is minor or not. Okay. So, but if there are, let's say, from the example, you can also see that if there are lots of pipe components, this one is 2.31 meters. If there are lots of pipe components, you add these KL values too. Okay, you can feel that from the example. Okay, now if I go back my previous formula here, I have found my HL value, so which is at 60.3 plus 2.31. 60.3 plus 2.31. Okay, so I have all of the values here. I have the mass flow rate, which is, so I've not calculated actually the mass flow rate. Now let's calculate the mass flow rate. Mass flow rate will be rho into V dot. And the rho of the fluid is 920 multiplied with 0.01, and it will be 9.2 kilograms per second. Okay. Now let's replace the values back here and get the pump power. So it will be 9.2. And all of the values are here. M dot here is also 9.2. And you can get the work dot pump useful. Okay. Now you can tell me the value of it. Work dot pump useful. And this is the pump work that you will need to carry water from one reservoir to the inlet, to the tank of the that is a truck, to the tank of the truck. So you can see that elbows here. You can have the two elbows here. Okay. This will be the pump work, but this is a useful pump work. But in real case, you have the efficiency problem. Therefore, that real pump work will be less than that one. So more than that one, sorry. Real one will be more than that one. Okay, let's wait. Okay, 6407.2 Alice's watts. And this is the useful one, but for the real one, you have 82%. Okay, therefore, work dot pump real. Okay, it will be that 6407.2 divided by 0.82. That will be the real one. Okay, now you can tell the real one. Okay. And 6 kilowatts, approximately 6 kilowatts of the pump, useful pump work you need. But the reality, it will be an actual one. The actual one, it will have, you will have the efficiency problem, and it will be that 7813 watts, or 7.8 kilowatts of pump we need to transfer oil from one to the, that is to the tanker. This is the end of the example. Okay, now let's see. There is one more example here. So I have how many minutes? I have 8 minutes. I can start it. So water is circulated from a larger tank. There is a large tank here through a filter. You have a filter here, and the back to the tank as shown here. This is the figure. The power added to the water by the pump is 200 feet Libre per second. We can convert it into the watt units. It is not a problem here, but the problem is how can we write the energy balance for the equation. And the KL values are given. For exit, it is 1. It is always 1. So if you remember our previous slide here, KL is always 1 because all of the energy is dissipated. It is always 1. And then you have the KL values for KL value for for elbow, and you have a KL value for filter. You can see it is 12. It's very large. You have the pump here. You have that 200 feet of 0.1 feet diameter pipe with epsilon by d is 0.1. Epsilon by d is also given. And yes, of KL valve, there is also a valve here which is 6, and the KL entrance is 0.8. These are the values that are given for the problem. Now let's solve the problem. To solve it, I should write the conservation of energy. Okay. To write the conservation of energy, what I will do is that I will take, you can take any 2 points, okay, any 2 points, but for closed systems, so this one is a closed cycle. You can see it sends the water to the reservoir and it sends back to the reservoir and sends it back. Okay. So I take 0.12 here, I take 0.1 here. The conservation of energy, and simplify the terms as possible, as much as possible. Okay. And if you write the conservation of energy, and you will have it that m dot, you will have P by rho and the plus V squared by 2G, V squared by 2, and the plus you have that rho GZ1, okay, and this one plus that work of the pump, which is useful part, and it will be equal to that m dot P by rho plus V squared by 2 and plus GZ2 and the plus the head losses, MGHF. My control volume to you, it is excluding the pump. You can see it here. The pump is not here. This is the control volume that I am considering outside the pump. And see, this outside, the pump is not in my control volume. My control volume is not included here. You can see now the control volume and the pump is here, and the point 1 is here and the point 2 is here. Or even you can take point 1 as here to make it simple to understand, and the point 2 is here. This is the inlet, point 1 is inlet, and the point 2 is outlet. Okay. And the fluid travels in that direction. Fluid travels in that direction and back to 2. Fluid travels in that direction and back to 2. Okay, and the P1 and the P2, they are not the same because they have the pump here, so they are not the same. And this inlet is for my control volume, not for the pump. This is outlet for the pump, inlet for control volume. Okay, but in reality, it is outlet for the pump, and this is outlet for control volume. You should note it, not the pump here. Okay, Z1 and Z2 are the same, and velocities are the same, and because the diameter is the same, D is same. Okay. And then now comes the pressure differences and this mgHl. Now let's write it. And if I divide each term by m dot, it will cancel out, and then you will have that. So you can see that the Z1 is the same as Z2. Okay. Here you have the same Z1, and here you have the same Z2. Therefore, Z1 and the Z2 cancels out. And then you have that P1 and the P2, there is a difference in pressure. Okay, the pressure is different from P1 and the P2 because this one is outlet of the pump and this one is the inlet of the pump. Therefore, you cannot erase these two terms here. And the velocity 1 and the velocity 2. And since the diameter of the pipeline is constant, therefore you will have that V1 is same as V2. Okay. Now comes that work done pump useful part. This is also 0. Okay. Question is to you, so is P1 plus HL is P2 or P1 is P2 plus HL? Okay, which one is true? Okay. P1 plus HL is P2, this one is the A, or P1 is P2 plus HL, this one is B. Which one is true for this problem? Is P1 plus HL is P2, so P1 plus HL is P2, or P1 is P2 plus HL? Let's see your value, the answers here. That says the first one. Okay, let's see one more answer. It says the B1, second one, sorry. Why the second one is the true? Why this one is true? Because fluid starts with some pressure of P1. Okay, this is the maximum pressure because it is outlet of the pump. And as it travels, the pressure drops. Okay, why it drops? It drops due to the friction. Okay, and therefore you will have that P2 plus friction. These two sums should be same as the beginning energy. The fluid begins with some total energy, which is P1. The total energy is the sum of the pressure at point 2, which is lost, which is decreased, and plus the frictional effects. Okay, so let me show as a graph here. So this one is the P. Yeah, that P is, you start with P1, that P1 drops. Why it drops? It should be, in reality, it should be constant. This part of the P1 is the head loss. And this one is of the P1 is P2. P2 plus head loss is the same as P1 due to added amount of the energy from the pump. Okay, so the true answer is of course B. So from the equation also, it is clear. So you will have that P1 will be, so I've cancelled out the terms here. P1 by rho will be equal to P2 by rho plus GHL. Okay. Now let's find the HL value here. And the HL value will be equal to FL by D V squared by 2G plus KL into V squared by 3G. Okay. And to find the F value, I will need the Reynolds number. Okay. I should find the Reynolds number will be that rho velocity diameter by mu. And then let me see how much time do I have. Let's stop it here. So next lecture I will continue from this example and find